IUPAC nomenclature of inorganic complex.
Yes, sir.
Uh, I gave you the guidelines on how to give the name of complexes. Okay. Okay. Now this is number 1, 2, 3, 4, 5, 6, 7, 8, 9. So how will you name the first one?
Tetracarbonyl nickel 4.
Tetracarbonyl nickel
4. 0.
Carbon monoxide is a neutral ligand. It does not have a charge. So it will be 0. How do you name this one? Second one.
Potassium hexacyanoferrate 3. Ferrate 3. Potassium
You have 6 cyanide. Gives 6 negative charge.
Yes.
You have 4 potassium. Gives you 4 positive charge. So you have to neutralize 2 negative charge.
Yes.
So iron has to be 2 plus. So potassium hexacyanoferrate 2.
2.
Next one.
Chromium 3
Ammonia is a neutral ligand, and I said ammonia to be named as amine, not amino.
Yes, sir. Yes, sir. Hexaamine, chromium chloride.
Hexamine, chromium 3 chloride.
Chloride.
4.
Sodium D, thiosulfato argentate 4.
Thiosulfate has 2 negative charge.
Yes.
So 2 thiosulfate will give me 4 negative charge. Sodium 3 plus will give me 3 positive charge. So what will be the oxidation state of silver?
Plus 1.
Because to neutralize 4 negative charge, I have to have 4 positive charge. 3 positive charge is given by sodium. So the remaining 1 negative charge to be neutralized by silver. So it should be named as sodium bis-thiosulfato, not dithiosulfato. Bis-thiosulfato argentate 1.
Yes.
Sodium bis-thiosulfato argentate 1. How do you name this one?
Sir, nitrogen.
Sir, pentamine, thiocyanato N,
Cyanide.
cobalt 3 chloride.
Right. Pentamine. There are 2 ways of naming it. Pentamine, isothiocyanato cobalt 3 chloride, because NCS has a negative charge.
Yes.
And 2 chloride gives 2 negative charge. So total 3 negative charge. So 3 negative charge will have to be neutralized by 3 positive charge. So ammonia is neutral. So the positive charge will come from the metal. So pentamine isothiocyanate cobalt 3 chloride, or what he said, pentamine thiocyanate hyphen nitrogen cobalt 3 chloride. Then this one.
Hexamine, cobalt 3, then hexacyanochromium 3. Sorry, hexacyanochromate 3.
Hexacyanochromate 3.
Chromate 3. Minus.
So number 6 will be hexamine cobalt 3 hexacyanochromate 3. 7.
Tetrapyridine, platinum,
7.
potassium,
This one.
platinum,
Potassium tetrachloroplatinum.
yes, potassium,
One at a time. I cannot hear it. All of you speak one at a time. From the behind. Come on. Tell me.
Potassium tetrachloride platinate 2.
Okay. That is one way. Another is tetrachloro, potassium tetrachloroplatinate 2, or potassium tetrachlorido platinate 2.
yes,
Okay, this one. Number 8.
sodium,
Sodium sodium tetrachloro aurate 3. Okay. Now the last one is this one.
tetrapyridine, platinum 2, then tetrachloroplatinate, platinate 4.
Tetrapyridine platinum 2, tetrachloroplatinate platinate 2, not 4.
Yes, sir. Yes.
Pyridine is neutral.
Now,
Like carbon. So tetrapyridine platinum 2, tetrachloroplatinate 2. Okay? Now this one.
diet.
Diamine chloride. Not amino. Diamine silver 1 chloride. Okay? Next.
Sodium
You have to identify correctly the oxidation state of the metal ion.
Yes.
Sodium dicyanide
Or
one. Okay.
Sodium carbonate.
Sodium carbonate, pentacyanide, ferrate,
One at a time.
Sodium carbonyl pentacyano ferrate 2.
Sodium carbonyl pentacyanoferrate 2. Correct. Okay.
Yes.
One at a time. One at a time. Tell me. Ah.
pentaaqua, nitrosilurium, sulfate.
Again, you try. Again, tell me.
Pentaaqua, nitrosilium, iron, 1 sulfate.
Good.
Yes.
So that's all about sodium. No, pentaaqua, nitrosilium, iron 1, sulfate.
Sulfate.
Okay. So we have done molecular orbital theory. Is it? We have done GACPR.
Yes.
Yes, sir.
Yes, sir.
Excuse me, sir. Sir, in that book JDV, they had given an explanation for the splitting of the orbitals as the ligands approach in different directions and increase the energy of those two orbitals of D. So I'm not getting that explanation.
In octahedral.
Yes, sir.
In octahedral geometry, suppose this is z-axis, this is x-axis, this is y-axis.
Yes.
The metal is at the center. The ligands are present along the y-axis, along the x-axis, along the y-axis. Now, there are 5 different orbitals of the d orbitals of metal.
Yes.
Out of the 5, dx square minus y square and dz square, they only point along x and y axis and z axis. And the ligands are also coming along the z axis, x and y axis. So which orbital will face the most repulsion from the ligand electron? Dx square minus y square. Similarly, dz square is pointing along the z axis and the ligands are approaching along the z axis. So which orbital will face the most repulsion? Dz square. That is why when they repel each other, they raise their energy. Whereas the other 3 orbitals, that is dxy, dxj and dyj, they are pointing in between the axes. They are not along the axis, between the Cartesian axis. As a result, the repulsion between the ligand electron and the metal electron will be less. That is why they are lower in energy, and these two are higher in energy.
Excuse me, sir.
Yes.
Sir, how can we differentiate between the water of crystallization and the water present as a ligand in a complex?
Okay. The lattice water and the coordinated water, there is no chemical test by which you can distinguish. Okay? You can distinguish by at what temperature the water molecules are lost. If it is lattice water, it will be anything between 80 degree to 110 degree. Whereas if it is a coordinated water, it will require a higher temperature because there is a metal dipole interaction, ion dipole interaction. So the coordinated water is held more firmly than the lattice water. The best answer comes from the X-ray structure. X-ray structure will let you know that the distance between the coordinated water and the metal ion will be shorter than the water between metal and the water and the metal ion. If it is not coordinated water, it will be at a longer distance. So there are two ways of determining. One is what temperature it requires to lose the water, and second, the best evidence comes from the X-ray structure, which says the coordinated water will have a shorter bond length than the lattice water. Is it okay?
Yes.
Now,
Sir,
bolo.
so in geometrical isomerism, for explaining that tetrahedral complexes do not show this geometrical property, it was said the relative position of the monodentate ligands attached to the central atom are the same with respect to each other. Tetrahedron is 3 downwards and 1 pointing upwards. So how is the relative position?
They have a fixed, they rotate very quickly. So all the positions are becoming equivalent. So the tetrahedral complex do not show geometrical outlines. Okay, is there any other question?
Excuse me, sir.
I cannot see. Oh, well.
So, iron combined with nitrosyl and nitrocilium in two different compounds, how can we calculate the oxidation state for the particular ferrum and for the particular NO group?
If there is a NO as well as NO plus, then your question is, how do we determine the oxidation state of the metal?
Yes, sir.
NO is neutral, just like CO. And NO plus has a positive charge. NO is paramagnetic, NO plus is diamagnetic. So you can easily determine whether you have NO or NO plus. But if both are present in a molecule, then it will show paramagnetism due to NO. There, you have to identify that how many NO are there as neutral and how many NO are there as NO plus. Then only we can calculate the oxidation state of the metal. Give me an example, I will tell you.
Sir, I don't have an example right now.
No, just let me give you. A hypothetical molecule I have written. Okay. What is the oxidation state of the metal? The negative charge is 3 negative charges. The chloride. Okay? You
Yes.
have 2 positive charge from the NO plus. Ammonia is neutral, NO is neutral. So the metal has to be one.
Yes.
That's how you practice.
It's
You have-
nomenclature.
Huh?
It's
Nomenclature.
nomenclature.
Diamine, nitrocell, dinitrocell, dinitrocelium, metal, let it be cobalt 1, chloride.
Yes.
Sir, can there be a pi bond in that coordination sphere?
Yes?
Sir, can you give an example?
Sometimes the hydroxide dam, for example, if you have
Count करेंगे क्या?
ammonia, ammonia can function as only sigma donor ligand because there is only one lone pair available. But NH2 minus there are 2 lone pairs.
Yes.
One is involved in sigma bonding to the metal, the other the pi bonding to the metal. So if you have more than one electron pair and if required, they can function as sigma as well as pi donor. Sigma donor, all ligands are sigma donor. But pi donor only when it has more than one lone pair. Because the first lone pair is required for sigma bond.
Sir, JDL asked that there is a solution. Then how can you infer from that a complex ion is present in it? Sir, if I take for conductivity in it, then it can infer that other electrolyte is also present.
Complex, if it is a cationic or anionic complex, it will conduct electricity. If it is a
Yes.
simple salt, it will conduct electricity. I have not used conductivity to distinguish from complex and electrolyte. I have used conductivity to distinguish for hydrate isomers, for differentiating neutral complex from anionic and cationic complex. I have not said that just because it conducts, that means I can differentiate from electrolyte. No. I
Sir,
can
then how can we predict that complex ion is present or not?
You have to estimate, you have to find out from analytical data that how many ligands, how many ammonia molecules are present, how many other groups are present, and the metal. So the molecular formula will tell you that whether it's a complex or that simple electrolyte. Now what is metallurgy? Metallurgy involves the extraction of metal from its source. That is called metallurgy. Metallurgical operation. All ores are minerals, but all minerals are not ores.
Yes, sir.
The minerals from which the metal can be extracted economically at a low cost, then it is called an ore. Now, metallurgical operation involves 2 types of metallurgy. One, the pyrometallurgy, and another, the hydrometallurgy. Pyro indicates Pyro means heat. And hydro means water. So, the metallurgical operation which involves heating comes under pyrometallurgy, and when they extract, the metallurgical operations are carried out in presence of water. That is called hydrometallurgy. In pyrometallurgy, it can be classified into three groups: calcination, roasting, smelting. Can you read what I have written?
Yes.
Okay. Calcination, write down. Calcination, heating of the ore below its melting point in absence of oxygen to remove moisture and to decompose metal carbonate to metal oxide and carbon dioxide. So to remove carbon dioxide from metal carbonate is known as calcining. I am repeating. Heating of the ore below its melting point in absence of oxygen to remove moisture and to remove carbon dioxide from metal carbonate is known as calcination. Second, roasting. Heating of the ore below its melting point in presence of oxygen to convert metal sulfide to metal oxide and sulfur dioxide. So what I said, heating of the ore below its melting point in presence of oxygen to remove or to convert metal sulfide to metal oxide and sulfur dioxide, to remove sulfur as sulfur dioxide, to remove arsenic as arsenious oxide. They are all volatile. That is known as roasting. So the roasting is basically heating in presence of oxygen but below the melting point of the ore to remove sulfur as sulfur dioxide, arsenic as arsenious oxide, and to convert metal sulfide as metal oxide and sulfur dioxide. Is it clear?
Yes, sir.
Okay. Smelting. The reduction of metal oxide by carbon at high temperature. Reduction of metal oxide by carbon at high temperature is known as smelting. For example, tin dioxide plus carbon. That is smelting. The reduction of metal oxide by carbon at high temperature is known as melt. Hydrometallurgy, the precipitation or the reduction of less electropositive metal. The reduction of less electropositive metal from its salt solution by the action of more electropositive metal is known as hydrometallurgy. So, in other words, I can say less electropositive metal is precipitated its salt solution by the action of more electropositive metal is known as hydrometallurgy. Do I repeat?
No, sir.
No, sir.
I can see the girl, she could not write it. Write down. Less electropositive metal, you write it fresh. Less electropositive metal is precipitated from its salt solution by the action of more electropositive metal. What is the action? The reduction. Yeah. By the reduction of more electropositive metal is known as hydrometallurgy. For example, copper sulfate plus iron. I take copper sulfate, dissolve it in water, and to it I add iron rod. What will happen? The iron is more electropositive than copper, so iron will reduce copper and form ferrous sulfate. How does it take place? Copper sulfate dissociates to copper 2 plus sulfate ion. Any salt will dissociate completely.
Yes, sir.
Iron will oxidize to iron 2 plus 2 electrons. Iron is more electropositive, so it will undergo oxidation. Copper 2 plus 2 electron to give you copper, which is precipitated. Ferrous ion combines with the sulfate ion to form ferrous sulfate.
Yes.
Okay, this is one example of. So you can see that the precipitation of copper has taken place from its salt solution by the action of more electropositive metal. So by the reduction with more electropositive metal, a less electropositive metal from its salt solution is precipitated, is known as hydrometallurgy. Okay?
Yes.
So more electropositive metal reduces the less electropositive metal from its salt solution is known as hydrometallurgy. For example, sodium just now you have named this complex, okay? Now this is water soluble. If I add zinc dust, zinc powder, zinc is more electropositive than gold.
Yes.
So zinc will go to zinc 2 plus, plus 2 electrons, and 2 gold 1 plus 2 electron will reduce to 2 gold, and zinc 2 plus will combine with 4 cyanide ions and 2 sodium ions. You have 2 sodium ions and each gold is associated with 2 cyanide. So 2 gold will have 4 cyanide ions. It will form Na2ZnCN4. Can you name this complex?
Yes, sir. Yes, sir.
Sodium So, zinc is more electropositive than gold. So, zinc has reduced gold class 1 to metallic gold. And zinc forms a complex which is water solid. So, gold is precipitated from its complex by the action of more electropositive metal. So more electropositive zinc will reduce less electropositive gold from class 1 to metallic gold. And this is carried out in presence of water. So it's an example of hydrometallurgy. Native ore, where the metal is present as metal itself in the ore. Copper, silver, gold. Why I circle gold? Because gold is exclusively, is only present in the form of native state, elemental state. But copper and silver, they are found both in the elemental state as well as in the form of. That is why, although these three are found in the elemental state, but these two can be found in their compound as well. But gold always in the form of metallic gold. Then oxide. Some of the oxide ores are like Fe2O3 is known as hematite. Fe3O4 is called magnetite. Fe3O4 is a mixed oxide. If you add FeO with Fe2O3, you get Fe3O4. So you have metal in two different oxidation states, 2 and 3. Bauxite. And tin dioxide is known as cassiterite. Sulfidose. Lead sulfide, zinc sulfide. Lead sulfide is called galena. Zinc sulfide is called zinc blende. Mercury sulfide has, there are two varieties of mercury sulfide. One is black, another is red. The red variety is called cinnabar, not the black variety. The red variety of mercuric sulfide is called cinnabar. CuFeS2 is called copper pyrite or chalcopyrite. Cuprous sulfide is called chalcocite or copper pyrite. FeS2 is called iron pyrite or fool's gold because it has golden yellow color, but it is not gold, so it is called fool's. Okay, write 4, this will write as 5. 4 is halido. Silver chloride is called horn silver. Potassium and chloride, magnesium chloride, hexawater hydrate is called carnallite. And sodium chloride is called rock salt. So these are few examples of oxysalts. That means the acid which contains oxygen is called oxyacids, and the salts derived from oxyacids is called oxysalts. Like nitrate, sulfate, carbonate, they are oxysalt because nitric acid is an oxyacid, sulfuric acid is an oxyacid, carbonic acid is an oxyacid because all contains oxygen atom in their acid. What are the reducing agents?
Which oxidize themselves.
What are the reducing agents used in metallurgy? Electrolytic reduction, there are two ways the metals are reduced. One, the fused salt, metal salt in the molten condition, when it is electrolyzed, it is called fused salt electrolysis. And this is actually when the metal is highly electropositive, like alkali metal, alkaline earth metal, aluminium, they are electrolyzed not from its solution but from its salt in the molten state. And that is why it is called fused salt electrolysis. The other is electrolytic reduction of salt solution, like copper sulfate. I can electrolyze copper sulfate to get copper at the cathode, because this is applicable only for less electropositive metal. So if the metal is less electropositive, then you can use a salt solution in aqueous medium. You can electrolyze to get the metal at the cathode. So, what are the examples of carbon reduction or carbon monoxide reduction? Tin dioxide plus carbon gives you tin plus carbon monoxide. Zinc oxide plus carbon gives you zinc plus carbon monoxide, where carbon is used as a reducing agent. Fe2O3 plus carbon monoxide gives you iron plus carbon dioxide. Well, carbon monoxide acts as a reducing agent. In a blast furnace react to give you iron and carbon dioxide.
Yes.
Aluminium is used as a reducing agent for thermite process. Do you know what is thermite process? The reduction of ferric oxide or chromic oxide by aluminium is known as thermite process. And the energy is liberated when aluminium reduces ferric oxide to iron or a chromic oxide to chromium. What can you infer from this reaction? We can say that aluminium has a greater affinity for oxygen than chromium or iron. As a result, the energy is liberated when it reduces iron or chromium from its oxide. That is called thermite process. So, after the reduction of the oxide or to the metal or electrolytic reduction, what are the purification methods? Liquation means you put the heart of the furnace you put the heart of the furnace in a slanting position. Put the metal, impure metal, on the top and you heat it from the below.
Yes.
The low melting metal will melt and trickle down, leaving the impurities behind. And this method can be applied only for metals which have low melting points. Tin has very low melting point 232. Lead has very low melting point 327. So if lead, tin and lead are associated with a high melting impurities, then when I put the ore in a slanting position and hit it from behind, the metal will melt and trickle down, leaving the impurities on the top. And that is called liquefaction process.
Yes, sir.